Okay, the problem is, using the graph below, determine the total work done. If the work was done in 2 seconds, what was the average power? So, work is the product of force and displacement. Now, if the force is a function of your position, then you can't just multiply. I mean, if you just said 50 newtons times 7 meters, you can get 350 joules, that would be wrong. Because at first, the force was very weak. It starts at 0. And then it gradually increases, and then it increases at a greater rate, and then the force stays the same. So this is some kind of weird mechanical device that can do work. And so, to solve this, here's what's given. I'll just put given. And then here's what we're trying to find. We're trying to find the work done, and then we're trying to find the power after when t equals 2 seconds. The average power. All right, so let's solve it. Okay, we have to integrate. We have to use integration. We say, well, okay, well, work is equal to force times displacement times the, times the cosine of the angle between. Let's just assume that this is 1, that the force and the displacement are parallel. But you think, well, it's just force times displacement. You can't use this because this force depends on what this is. Whenever that happens, you have to integrate. And in your calculus classes, you learn all kinds of fancy integration techniques. When you have force as a function of x, and you can go through the whole thing. But in this class, we won't ever need to do that because it's either going to be triangles or rectangles. So the integral is the area underneath there, the area there, the area there, and the area there. So the work done is just going to be equal to this triangle, which is 1/2 the base, which is 2 meters, times the height, which is 20 newtons, plus, well, we got this little rectangle here. The base is 1 meter, times the height is 20 newtons. And then we got this little triangle right here. I'll just put it down here. Plus 1/2, because it's a triangle, the base, which is 1 meter, times height. Well, we went from 20 to, see, 20, 30, 40, 50. So we went up 30 newtons, right? Is that right? Agree with that? And then plus, and now we have this big thing right here. And this is 1, 2, 3, 4. And it's a rectangle, so it's just 50. And so the work is, well, this is just 20 joules plus 20 joules. And this is plus 15 joules. And this is plus 200 joules. So 20 plus 20 is 40, 50, 55. So the work is 255 joules. And power, to figure out the average power, this is not the instantaneous, but the average power. The power is just the total work done, or the energy transferred in how much time. So it's 255 joules divided by 2 seconds. So that's what? 1, and then that's 2, and and then goes into what? Is that right? 127.5? Is that right? Now, what are the units for this answer? Yeah, that's what I said. Watts are the units for this answer. Thank you. I've been waiting all year to tell that joke, and all right. Or 0.5, or you can say 128, I suppose, or 127.5. Watts. Now, you probably should round that off to 128, or even, because there's two significant figures here, 130 watts, but you guys don't do that. This bothers me. That's too many significant. I'll just say 128. I'm not going to mark it wrong. All right. So here's how this is graded. Wait, before we get to that, again, remember that work is the area underneath a force versus position graph. Force times displacement, which is a change in position, and that's the only way to do it if your graph looks like this. And by the way, even if you were in a calculus class and you knew all those fancy calculus techniques, you'd still do it this way because this is some kind of weird piecewise function. And remember that power is work over time. So this is the rate. On average, they were putting out 128 joules of energy per second. Okay, so that's what that means. Any questions?